This is another example, so we will see the how we can do it in Excel. Wage, trying to find what is the effect of the education on wage, and then you can fit it. So same way, this is the how much the one more year of education. This is number of year education. One more year of education, your wage will go up by 0.54. Okay, so this is hourly wage. So hourly wage can go up $0.54. In the intercept is the if there is a zero education, what would be your salary? But actually, you cannot. Again, you will not have a zero education years of the person. So this will not be the real data there. However, this is since we have to draw the line here. Of course, even though we don't have a data point here, so what if this is keep going on? Then where it located? So you can use this regression model, again, the statistical model here, and then we can predict what would be the wage. But again, as we talk about it, we don't know the real one, but I can tell my prediction will be the mean of the wage in that given number of years of education. Okay, now the example 3 is the example voting outcome and campaign expenditure. So if you spend more money, you are expecting getting more vote, right? So, but how much? This is you can see the share A is a percentage of campaign expenditure candidate A, and then this is a percentage of the vote for the candidate A. Then you can compare the percentage versus percentage. What will be the effect of the share A, percentage of campaign expenditure on the percentage of vote for the candidate A? So this is like this, right? So the result is looking like this. So 1%, if you spend 1% more, then you're getting vote is a 0.464% point. You can get more. So if you share increase 2 point, then roughly you can get about the 1% increase on vote. But what is this intercept is, again, if you don't do, theoretically, if you don't do any campaign expenditure, so you don't spend any money, 0%, then what would be the percent? So this vote start from the 26% point, and then it will go up as you spend more money, increase the percentage of the expenditure. Property of the OLS is an ordinary least square on any sample data. So y hat is the fitted or predicted value, okay? And then if you just calculate the actual, this is actual data. This is from model. Then difference will be the what we call the residuals. Residual means is there is something we cannot cover up. Here using my statistical model, this model cannot cover up something because there will be a lot of different factors to affect y. So that will be what we call the residuals. And algebraic property will be the summation. All the summation should be 0. Why is that? Because if you divide by n here, this will be the expectation of u, right? This should be 0. That's why it should be 0. And covariance between the x and u should be 0 because the u should not contain any information of x. If x can explain u just a little bit, that which means is your beta 1 is not fully capture the effect of x. the x value, right? That's why if you, the better one, take a full effect of the x variable, then u cannot be explained by x, so which means covariance should be 0. And then sample average of y and x, also average x, should be on the regression line. Yeah, obviously that's true, intuitively true. So once you find the line, regression line, then we have to evaluate how good the line is. So we call this is goodness of fit. So how good my line fit the data. So how well does the explanatory variable explain the dependent variable? How much? So we will find out the measure of variance. Actually, we already seen this SSE and SSR in the F statistics. So this is a total. So total means it's a total difference, right? So total sum of square. So how much difference from Y? Y is from Y bar. This is a more like a Y variables standard deviation. Again, this is not variance at all, but similar to the variance. Here, this is the, instead of the real Y, this is actual Y. This is the estimated, no, explained. That's why this is explained, right? From model. And then you can calculate the variance here. And then U is the residual, R is the residual. And once you find out the T, so this is the residual is the all other factor. The effect of the right. This residual will contains the other factor other than my x. This error term contains all factors from all other factors. It's contained here, and then this is the model we can explain using my model, right? My variable. So my variable can explain the real data y, but this much, and then all other factors we don't know or we cannot measure. It's which is contained by this error. So if you add up this explained and then this is like unexplained, or I don't know if there's a word like this, but not explained factor and explained by the model factor. If you add up, this should be the total sum of square. So my sum of square SST, that's what it means. SST should be SSE plus SSR. So this is how much we can explain by model, and this is the all other factor than my model. Together, if we add up, then that's the total sum of square. Now we define the R square, so ST total variation is the explained part and unexplained part together. That's a total. We calculated R square. So R square is trying to capture how much we can explain. So among the total, how much the my explain has a variance. So total variance, and then how much our model can cover up in proportion or ratio. This is R square. Okay, so high R square means my model explain more on the true value of y. So this is R square coefficient and the coefficient of the determination. So this R square, the official name is a coefficient of the determination, but usually we call just this R square. So what we can do is we can find out this is R square, SST is the real Y. This point is the all real Y, actual Y. This is YI. Right? So since we calculate the square, the difference, so this is the difference between yi minus y bar, right? And then you take square, that's area. And here f is our model. So this point is actually the y hat. Okay, and then this point is the y I. Yeah. And the calculation. So how much my model can explain? No, that's the residual part. Right? This is a residual. This difference is the y hat minus y. This is the residual, and then the area of the square is the square. So how much the residual you have? So this is a residual divided by t, and then if you subtract from 1, then you can tell y r square is how much our model can explain. R square is the same as the rho square. This is a person. Usually we don't call it. This is just correlation coefficient. Difference between this rho correlation coefficient and R square is R square only can have a value 0 to 1 because it's a square. Since this is square, it can be only 0 to 1, but rho can have a minus 1 to 1. Minus 1 means it's a perfectly negative correlation, and plus 1 is a perfectly positive correlation. But if you have some number which is less than, greater than 1 but less than 0, and yeah, relationship is negative but it's not perfect. And something like this is you don't have a close to 0 number because it doesn't seem like a relationship exists. And this one, obviously there's clear pattern, but because rho is only care about the linear. In terms of linear, yeah, it seems like there's no relationship. There's no linear relationship there. And there's adjusted R. So if you look at the result of the Excel regression, then you will see the adjusted R. So what is adjusted R? Actually, for the simple regression, adjusted R, you don't need it. Usually when we just talk about how much my model can explain the dependent variable, we don't need to use adjusted R. The when we use adjusted R is the when you're trying to find out, do I have to add one more variable? Whenever the regression, if you add one more variable, your R square is always going up. Really worst case is the R squares stay the same. So you cannot make it worse. Even though you put it in the totally meaningless variable, still your R square will increase a little bit. Right? So when we decide, so we will just see the later chapter, but so trying to find out how much we can explain considering the how many variable we are using here. Okay, so if you put the pretty meaningless predictor, this adjusted R scale will goes down. So you can compare when you want to compare. Do I have to add this variable or not? Then you have to look at the adjusted R. So how to calculate adjusted R is kind of complicated here. And then here the K is the number of predictor. So here, which is axis, right? So x1, x2, x3, so how many? number of predictors variable. So whenever you have a more and more, yeah, actually you can calculate it. Right? Since this is a denominator, when you have a more and more, so your denominator is getting smaller and smaller. So this number is getting bigger and bigger, and you are subtracting the bigger number, which means your R, adjusted R square will goes down. So how can I get a R square, adjusted R square goes up when you put the one more predictor variable? Is the you have to improve your R square significantly. The new variable should have enough contribution to the prediction so that then you can have a higher R, adjusted R square. So when you have to compare models, the other model has more variables, and you can tell is it worth to put more additional variable or not. So we will use adjusted R again in the when we talk about the model selection. Okay, this is the R square will be also calculated again. Even though we already look at all other the complicated numbers, but actually the computer will bring up to this number. You don't have to calculate it by yourself. And then this is the R square example, and you can see it doesn't explain that much. So ROE doesn't explain the salary that much. Maybe there's a bigger factors outside of the other than the ROE, right? However, here this one, how much the percentage you spend on the expenditure will explain the vote of A about 85%. So regression model, this model explain 85%, about 85% of the total variance. So how much the vote, what is the percentage of vote the candidate A will get can be explained by about 85% can be explained by the percentage of expenditure spent. However, here ROE cannot explain the salary that much. But that does not mean ROE doesn't have an effect. Okay, it just simply said there is the other factors. Maybe there's a lot of different other factors or one big other factors, but there is many other factors will change the salary rather than the ROE. But clearly, this does not mean ROE doesn't have a effect. That's why we do the F test and the T test. That's a totally different. This has a significant effect on the salary or not. You have to look at the T test or F test. This is just how much ROE can explain the salary.